Have you ever looked up at the night sky and felt that tug of wonder, the sense that there's something vast and mysterious just beyond our grasp? Light bends around invisible forces, stars flicker with secrets older than time, and the very fabric of space seems to ripple with unanswered questions. This isn't just poetry, it's the reality of our universe, a cosmic playground where light and gravity perform an endless dance, leaving behind riddles that defy easy explanation. For centuries, these puzzles have tantalized the greatest minds, from Einstein staring into the abyss of relativity to modern astronomers chasing the echoes of the Big Bang. And yet, the more we uncover, the more we realize how much remains hidden in the shadows. Today, we're setting off on a journey to explore the 30 universal riddles of light and gravity, those mind-bending phenomena that shape everything from the birth of galaxies to the way your phone's GPS stays accurate. Think about it. Every time light curves around a black hole or gravity tugs at the edges of space-time, it's not just a scientific curiosity, it's a clue to the universe's grand blueprint. These aren't abstract ideas locked away in textbooks. They're the forces that sculpt our reality, weaving the invisible threads that hold existence together. Why does light slow down in water? How can gravity be both the weakest and most relentless force in the cosmos? The answers aren't just fascinating, they're foundational, touching everything from how we understand time to the very fate of the cosmos itself. So let's take this step by step, unraveling each enigma like detectives piecing together a celestial crime scene. Along the way, you'll discover how black holes act as cosmic prisms, why dark matter might be the universe's hidden architect, and even how the glow of distant stars carries messages from the dawn of time. This isn't just a list of facts, it's an invitation to see the universe with fresh eyes, to stand in awe of its complexity and maybe, just maybe, catch a glimpse of the hidden logic behind it all. By the time we're done, you won't just know more about light and gravity, you'll feel them, the pulse of the cosmos, whispering its secrets to those willing to listen. Ready? Let's begin. Imagine a race where every runner, no matter how fast they sprint, can never outpace a beam of light. It sounds like science fiction, but this is the universe's ultimate rule. Light speed isn't just fast, it's the unbreakable barrier etched into the fabric of reality itself. Einstein's theory of relativity didn't just give us this speed limit, it revealed something far stranger. No matter how fast you're moving, light always zips away from you at the same relentless pace, about 1 billion kilometers per hour. Toss a flashlight on a speeding train and its beam races ahead at light speed, not a fraction faster. This isn't just about optics, it's a cosmic decree that bends time, warps space, and keeps causality from unraveling. But why can't we break this barrier? The answer lies in the universe's ledger of energy. As objects accelerate, they're mass balloons, demanding more and more energy to push them faster. Approach light speed, and the energy required becomes infinite, an impossible tax no object can pay. Yet the universe loves teasing us with loopholes. Take tachyons, hypothetical particles born already faster than light, slipping through equations like ghosts, or wormholes, cosmic shortcuts where space-time folds like paper, letting you cheat the speed limit by bending the road itself. These aren't just plot devices for sci-fi, they're serious theories that physicists wrestle with, probing the edges of known physics. And here's the real twist. Light speed's constancy isn't just a limit, it's the glue holding reality together. If information could outpace light, cause and effect would crumble. You could see a supernova explode before the light reached you, or worse, receive a message from the future. The universe guards this speed limit fiercely, not out of spite, but because breaking it would unravel the very logic of existence. Yet every time astronomers spot a distant quasar or measure gravitational waves, they're testing this limit, searching for cracks in the cosmic rulebook. Because if light speed ever falters, the universe as we know it might just rewrite itself. Gravity is the universe's ultimate ghost story, an invisible hand that reaches across the void, tugging planets into orbit, binding galaxies together, and even bending the path of light itself. But here's the eerie part: it does all this without touching anything. Newton called it action at a distance, a phrase that sounds more like magic than physics. How can the sun, 93 million miles away, pull Earth toward it without so much as a cosmic string connecting them? For centuries, this was the puzzle that haunted scientists until Einstein stepped in and rewrote the script. His revelation: gravity isn't a force in the traditional sense at all. Picture spacetime as a trampoline, with stars and planets creating dimples where they sit. Roll a marble near one of those curves and it'll spiral inward, not because some mysterious force is pulling it, but because the fabric beneath it is warped. This is gravity's true face, the curvature of spacetime itself. When you trip and fall, you're not being pulled down, you're just following the path carved by Earth's enormous weight pressing into the cosmic canvas. Yet for all its cosmic influence, gravity is embarrassingly weak compared to the other fundamental forces. A tiny fridge magnet can override Earth's entire gravitational pull on a paperclip. Why? One theory suggests gravity might leak into extra dimensions we can't perceive, diluting its strength in our observable universe. Or perhaps it's simply a matter of scale. While electromagnetism binds atoms tightly, gravity's domain is the vast, slow dance of celestial bodies. The plot thickens with gravitational waves, ripples in spacetime detected for the first time in 2015. These waves, born from cataclysmic events like colliding black holes, are the universe's way of sending smoke signals, proof that spacetime isn't static but vibrates like a drumhead. And then there's the holy grail, quantum gravity. While the other forces play nice with quantum mechanics, gravity stubbornly resists, leaving physicists scrambling to reconcile Einstein's smooth spacetime with the chaotic quantum realm. String theory, loop quantum gravity, and other bold ideas vie for the title of theory of everything, but so far the mystery persists. What's at stake? Everything from the birth of the universe to the fate of black holes. If we crack gravity's code, we might finally understand why the cosmos looks the way it does, or uncover entirely new layers of reality hidden in plain sight. For now, gravity remains the universe's most persistent riddle, a whisper in the dark, asking us to listen just a little closer. There's a cosmic thief at large, stealing starlight and warping galaxies, yet we've never seen its face. This isn't the plot of a sci-fi thriller. It's the dark matter enigma, one of the universe's most baffling puzzles. Imagine an invisible scaffold holding up the cosmos, its presence betrayed only by the way it tugs on everything we can see. Galaxies spin so fast that their outer stars should fling into the void, yet something unseen grips them tight. Light bends around empty patches of space as if ghostly hands are twisting the lens. Even gravity's equations come up short, demanding 5 times more matter than all the stars, planets, and cosmic dust combined. That missing mass, dark matter, the universe's silent architect, weaving its influence through the darkness. The clues started piling up in the 1930s when astronomer Fritz Zwicky noticed something odd about the Coma cluster. Galaxies within it moved so fast that their collective gravity shouldn't have held them together, yet there they were, defying the math. Decades later, Vera Rubin's observations of spiral galaxies confirmed it. Stars at the edges orbit just as fast as those near the center, like a vinyl record spinning rigidly instead of slowing toward its rim. According to Newton's laws, this shouldn't happen unless extra mass lurks in the galactic shadows, anchoring everything with its invisible pull. But how do you hunt something that doesn't emit, reflect, or absorb light? Physicists have turned the cosmos into a detective's toolkit. Gravitational lensing, where dark matter bends light from distant objects, acts like an X-ray, revealing the skeleton beneath the universe's skin. Particle colliders like the Large Hadron Collider smash atoms at near-light speeds, hoping to shake loose a dark matter candidate. Underground labs, shielded from cosmic noise, listen for the faintest whispers of interaction. And yet, after decades of searching, dark matter remains stubbornly anonymous. Is it WIMP, weakly interacting massive particles that barely graze ordinary matter? Or actions, feather-light particles born from quantum field quirks? Maybe it's something even stranger, a shadow universe with its own rules entirely. The stakes couldn't be higher. Without dark matter, galaxies wouldn't have clumped together in the early universe. Life might never have had a chance to form. Yet its elusiveness taunts us a reminder that most of reality isn't just unknown, but unknowable by ordinary means. Every flicker in a detector, every anomalous bend of starlight, brings us closer to rewriting the cosmic ledger. Until then, dark matter lingers like a riddle whispered in the dark, challenging us to rethink everything we thought we knew about the weight of the universe. If dark matter is the universe's hidden anchor, dark energy is its silent rebellion, an enigmatic force pushing the cosmos apart faster than anyone predicted. Picture a loaf of raisin bread baking in the oven, with each raisin representing a galaxy. As the dough expands, the raisins move apart. Now imagine the oven suddenly turns up the heat, and the raisins start racing away from each other at an ever-increasing speed. That's the universe we live in, not just expanding, but accelerating. And the culprit behind this cosmic speed-up, dark energy, a phantom presence so mysterious it makes dark matter seem almost familiar. The story begins in the late 1990s, when two teams of astronomers observing distant supernova made a startling discovery. These exploding stars, used as cosmic mile markers, were fainter than expected, meaning they were farther away than the standard model of the universe predicted. The only explanation, the expansion of space, wasn't slowing down due to gravity, as everyone assumed. It was speeding up, as if some invisible hand were pressing harder on the gas pedal. This revelation flipped cosmology on its head, earning the researchers a Nobel Prize and leaving the rest of us with a haunting question: what could possibly overpower gravity on such a colossal scale? Enter Einstein's cosmological constant, a term he originally added to his equations to keep the universe static, later calling it his greatest blunder when Edwin Hubble proved the cosmos was expanding. Now it's back with a vengeance, repurposed as the leading candidate for dark energy. Think of it as the energy inherent to empty space itself, a relentless pressure that grows stronger as the universe expands, creating more space, which in turn fuels more dark energy. It's a feedback loop with no off switch, stretching the fabric of reality thinner with every passing eon. But the cosmological constant isn't the only suspect. Some theories suggest dark energy might be a dynamic field, like an invisible ocean with currents that change over time. Others propose it's a sign of extra dimensions leaking into our own, or even a flaw in our understanding of gravity on cosmic scales. The most unsettling possibility, the Big Rip, a scenario where dark energy's push becomes so dominant that it tears apart galaxies, then stars, then atoms, reducing all of existence to a sea of lonely particles drifting in the void. Yet for all its apocalyptic potential, dark energy is eerily subtle. Its density remains constant even as the universe grows, making it 10 billion times weaker than a proton's energy in a teaspoon of space. This faintness is precisely what makes it so hard to study. Current experiments like the Dark Energy Survey and the upcoming Euclid Space Telescope map millions of galaxies to trace its influence, while quantum physicists hunt for its fingerprints in the vacuum's fleeting energy fluctuations. What's at stake isn't just the fate of distant galaxies, but the very nature of reality. If dark energy's strength changes, it could rewrite the universe's destiny, turning the Big Rip into a Big Crunch or even a cyclical rebirth. For now, it remains the ultimate cosmic wildcard, a reminder that the universe isn't just expanding, but running away from us, carrying its deepest secrets into the dark. Black holes aren't just cosmic vacuum cleaners, they're the universe's ultimate puzzle boxes, swallowing matter, light, and even the rules of physics as we know them. But here's the twist. What happens to all that information, every atom, every particle, every shred of data, when it crosses the event horizon? According to quantum mechanics, information can never truly disappear. It might get scrambled, but it's always preserved. Yet black holes seem to defy this rule, compressing everything into a singularity where space and time break down. This contradiction is the heart of the information paradox, a problem so profound it split physicists into warring camps for decades. Stephen Hawking threw the first grenade in the debate when he calculated that black holes aren't entirely black. They emit a faint glow of radiation, now called Hawking radiation, slowly leaking energy until they evaporate entirely. But here's the catch. That radiation appears random, carrying no trace of the original material that fell in. Imagine burning a library full of books and claiming the smoke particles contain no information about the stories they once held. That's the crisis if Hawking radiation is truly random. The universe's ledger of information is being erased, violating quantum law. Cue the firewall paradox. Some theorists argue that the event horizon isn't the gentle boundary we once thought, but a searing wall of energy that incinerates anything crossing it. This firewall would preserve information by destroying infalling matter before it reaches the singularity, but it creates another problem. Einstein's relativity insists that crossing the event horizon should feel uneventful, like floating into a calm river. You can't have both. Either relativity is wrong or quantum mechanics is. Then there's the holographic principle, a radical idea that suggests the information isn't lost at all. It's just encoded on the black hole's surface like a cosmic hard drive. Picture a three-dimensional object projected onto a two-dimensional screen. Every detail is preserved, just rewritten in a new language. If true, black holes might be nature's ultimate storage devices, packing the information of entire stars into shimmering patterns on their event horizons. The stakes: if information can vanish, our entire understanding of causality collapses. Every experiment, every calculation, every prediction in physics relies on information being conserved. Solve this riddle, and we might unlock the secret to merging quantum mechanics and gravity, or discover that the universe plays by rules we've yet to imagine. Until then, black holes remain the ultimate cosmic conundrum, swallowing not just matter, but the very foundations of reality itself. Picture this: you and your identical twin part weighs one boards a spaceship hurtling near light speed, while the other stays on Earth. Decades later, you reunite, only to find your sibling has aged far slower than you. This isn't a sci-fi plot twist. It's the twin paradox, a real consequence of Einstein's theory of relativity that bends time itself like a rubber band. The faster you move, or the closer you linger to a massive object like a black hole, the more time crawls for you compared to everyone else. It's as if the universe has its own set of invisible hourglasses, each ticking at different speeds depending on where or how fast you're standing. But how does this actually work? Think of space-time as a vast, stretchy fabric. Gravity doesn't just pull objects, it tugs on time too. Near a black hole's crushing grip, time stretches thin, slowing to a near standstill from an outsider's perspective. Meanwhile, high-speed travel compresses time's flow like a squeezed accordion. Here's the mind-bending part. Both twins would swear their own clocks are running normally. It's only when they reunite and compare notes that the discrepancy slaps them in the face. This isn't an illusion, it's the universe's way of keeping the speed of light constant for all observers, no matter their motion. The implications ripple far beyond theoretical puzzles. GPS satellites orbiting Earth have to account for time dilation, adjusting their clocks to stay synced with the ground. Without these corrections, your navigation would drift off by miles within minutes. Even your head ages infinitesimally faster than your feet, thanks to Earth's gravity tugging harder down below. These effects are tiny but undeniable proof that time is fluid, not absolute. Now, let's crank the weirdness up a notch. Imagine diving toward a black hole's event horizon. To a distant observer, you'd appear frozen in time, your signals redshifted into oblivion. Yet for you, time flows normally until tidal forces shred you apart. This bizarre disconnect reveals a startling truth. There's no universal now. Your present moment might be someone else's distant past or future, depending on motion and gravity. It's as if the universe is running countless versions of reality simultaneously, each out of sync with the others. So what's the takeaway? Time dilation isn't just a quirk of physics. It's a window into the universe's deepest workings. It tells us that time isn't a backdrop, it's an active player, woven into the fabric of space, shaped by speed and gravity. Every second we experience is a negotiation between our place in the cosmos and how we move through it. And if that doesn't make you pause the next time you check your watch, consider this. Somewhere out there, a twin might be living your future right now. Einstein once called it spooky action at a distance, a phrase that perfectly captures the sheer strangeness of quantum entanglement, the phenomenon where two particles become so deeply linked that changing one instantly affects the other, no matter how far apart they are. Imagine tossing a pair of gloves into opposite ends of the universe. Open the left glove to find it's right-handed, and instantly, without any signal or delay, the right glove knows to become left-handed. This isn't science fiction, it's quantum mechanics at its most baffling, defying our everyday intuition about how the universe should work. The heart of the mystery lies in what physicists call non-locality. In our macroscopic world, influences travel at or below light speed, a cosmic speed limit Einstein held sacred. But entangled particles seem to flout this rule, coordinating their behavior faster than light could ever bridge the gap between them. When scientists measure one particle's spin or polarization, its entangled partner snaps into a correlated state, as if flipping a switch in two places at once. The wildest part, this happens even if the particles are light years apart, with no known mechanism connecting them. It's as though the universe maintains a hidden hotline, bypassing space-time entirely. Experiments have confirmed this repeatedly, starting with John Bell's groundbreaking work in the 1960s. His theorem laid out a mathematical way to test whether entanglement could be explained by hidden variables, secret instructions the particles carry from birth. The results were unequivocal. No local hidden variables could explain the correlations. Subsequent tests, like the famous 2015 loophole-free experiments, sealed the deal. Entanglement isn't a quirk of imperfect setups. It's woven into the fabric of reality. But how? One interpretation suggests particles aren't truly separate once entangled. They exist in a shared quantum state, a single entity stretched across space. Measure one part and the whole system responds. Others propose that entanglement reveals a deeper layer of reality where space and time emerge from a network of quantum connections, like threads in a vast cosmic tapestry. Then there's the holographic principle, hinting that our three-dimensional universe might be a projection of entangled information encoded on a two-dimensional surface. The implications are staggering. Quantum encryption already exploits entanglement to create unhackable codes. Any eavesdropper would disturb the delicate link, alerting the users. Future quantum networks could teleport information across the globe, not by moving particles, but by leveraging these ghostly correlations. Some even speculate that entanglement might hold clues to quantum gravity, bridging the chasm between relativity and quantum mechanics. Yet for all its promise, entanglement remains deeply unsettling. It forces us to confront the possibility that reality isn't as local or independent as it seems, that beneath the familiar world of separate objects and clear boundaries, the universe is profoundly interconnected, whispering secrets we're only beginning to decode. Einstein may have called it spooky, but perhaps it's just the universe reminding us there's far more to existence than meets the eye. The universe is unimaginably vast, a sprawling ocean of stars with billions of planets nestled in habitable zones where liquid water could pool and life might take root. Given those odds, the Milky Way alone should be teeming with civilizations, their radio signals buzzing through the void like cosmic chatter. And yet, when we point our telescopes skyward, all we hear is silence. No alien broadcasts, no interstellar artifacts, not even a single microbial fossil from another world. This eerie absence is the Fermi paradox, a riddle that asks, if life is statistically likely, why does the cosmos feel so empty? One chilling answer is the Great Filter, a hypothetical barrier that prevents life from advancing to interstellar stages. Maybe the filter is behind us, an improbable fluke that made life on Earth staggeringly rare. If so, we might truly be alone, but the more unsettling possibility is that the filter lies ahead, a catastrophic bottleneck like self-destructive technology or runaway artificial intelligence that wipes out civilizations before they can spread. Every silent exoplanet could be a graveyard, a warning written in the stars. Then there's the zoo hypothesis, the idea that advanced civilizations deliberately avoid contact, observing us like animals in a cosmic wildlife preserve. It's a comforting thought until you consider the darker twist. What if they're not benevolent researchers but cautious predators, hiding until we're no longer a threat? Alternatively, we might be like ants trying to perceive human cities, too primitive to recognize the megastructures or communication methods of a galaxy-spanning culture. Or perhaps the truth is simpler. Life might arise easily, but intelligence like ours could be a freak accident, a roll of the evolutionary dice that rarely repeats. Dolphins and octopuses are brilliant, but they'll never build radios. Even if other worlds host life, it might be stuck in microbial slumber forever. The silence humbles us. It forces us to confront our assumptions about life's inevitability and our place in the cosmos. Every search for extraterrestrial intelligence, every probe sent to Mars, is a plea thrown into the dark, a hope that somewhere, someone else is listening too. Until then, the Fermi paradox remains the universe's most profound cold shoulder, a riddle wrapped in the quiet between the stars. In the vast emptiness of space, where every movement follows the precise rhythms of gravity, two tiny spacecraft defied expectations and left scientists scratching their heads for decades. NASA Pioneer 10 and 11, launched in the early 1970s to explore the outer solar system, became the center of one of astronomy's most stubborn mysteries, the Pioneer Anomaly. As these probes hurtled toward the edges of our cosmic neighborhood, tracking data revealed something bizarre. They were slowing down ever so slightly, as if an invisible hand were tugging them backward. Not by much, just a fraction of a nanometer per second squared, but over years and billions of miles, that tiny discrepancy added up. The laws of physics said it shouldn't happen. So what was pulling on the pioneers? At first, researchers suspected mundane explanations. Maybe it was fuel leaks or uneven thermal radiation from the probe's nuclear power sources gently pushing them off course. But meticulous calculations ruled those out. The deceleration was too consistent, too uniform, as if some unseen force were at work. The anomaly clung to the pioneers like a shadow, vanishing only when they passed beyond Saturn's orbit. That detail fueled wilder theories. Could it be evidence of dark matter's gravitational tug, or even a flaw in our understanding of gravity itself? Einstein's general relativity had been tested relentlessly, but here was a glitch it couldn't explain. The breakthrough came from an unexpected source, heat, not from the cosmos but from the probe's own design. Pioneer's dish-shaped antennas acted like radiators, emitting infrared radiation as they expelled waste heat. Scientists realized this thermal glow wasn't perfectly symmetrical. It bounced off the back of the antenna dish unevenly, creating a tiny but constant recoil force. Picture blowing on a toy sailboat. Even a faint, steady breath will nudge it forward. In Pioneer's case, the effect was minuscule but cumulative, matching the mysterious deceleration almost perfectly. Case closed, not quite. While thermal radiation explained most of the anomaly, some researchers argue it doesn't account for every last bit of drift. That lingering uncertainty keeps the door cracked open for more exotic possibilities, like modifications to gravity at extremely weak accelerations, a theory called modified Newtonian dynamics, or MEND. Others wonder if the anomaly hints at unseen mass in the outer solar system, a ghostly presence subtly altering trajectories. The Pioneer anomaly is more than a cosmic whodunit. It's a lesson in humility. Even our most precise instruments can behave unpredictably, and sometimes the answer isn't new physics, just a quirk of engineering we overlooked. But it's also a reminder that the universe loves to surprise us. Every unexplained twitch in the data, every tiny deviation, might be the first whisper of something far bigger lurking in the dark. And that's why scientists keep looking, because the next anomaly could rewrite the rules entirely. The universe is supposed to be fair, no favorite directions, no privileged viewpoints, just an even playing field stretching endlessly in all directions. That's the cosmological principle, a cornerstone of modern astronomy. But when scientists peered into the afterglow of the Big Bang, they stumbled upon something that shouldn't exist, a lopsidedness in the cosmos so unsettling it earned the nickname, the axis of evil. This cosmic oddity lurks in the cosmic microwave background, the faint echo of the universe's fiery birth. Imagine the CMB as a baby picture of the cosmos, a snapshot from when it was just 380,000 years old. In theory, its temperature fluctuations should be random, like static on an old TV, no patterns, no preferred alignment. Yet when researchers mapped it, they found a bizarre asymmetry. One half of the sky appears slightly warmer than the other, as if the universe tipped its hat to a particular direction. Even stranger, some of the larger fluctuations seem oddly aligned with our solar system's plane, like cosmic breadcrumbs pointing back at us. The implications are staggering. If the asymmetry is real and not some fluke of measurement, it challenges the very idea that the universe is isotropic, the same everywhere. One possibility is that we're seeing fingerprints of something primordial, a structure or condition that predates the Big Bang itself. Some theories suggest our universe might be one bubble in an infinite multiverse, and the axis of evil marks where our bubble brushed against another. Others propose exotic physics like a spinning universe or a gravitational tug from a neighboring dimension. Then there's the humbling alternative, maybe we're the anomaly. Our solar system's motion through the cosmos could be imprinting this pattern onto the CMB, like a fingerprint smudging a lens. If true, it would mean the axis of evil isn't a feature of the universe, just a reflection of our own backyard. But that explanation feels too convenient, almost like the medieval idea that Earth sat at the center of creation. The mystery deepens when you consider quantum fluctuations. In the early universe, these tiny ripples should have been random, yet the axis of evil hints at a preferred direction, as if cosmic dice rolled the same number too many times. Could there have been a pre-Big Bang phase that set this asymmetry in motion? Or does it point to a fundamental flaw in our understanding of inflation, the process that smoothed the universe into its current state? For now, the axis of evil remains one of cosmology's great unsolved puzzles. It taunts us with the possibility that the universe isn't as uniform as we thought, or worse, that we're seeing it through a distorted lens. Every new observation, from Planck satellite data to next-generation telescopes, brings us closer to an answer. But until then, this cosmic imbalance stands as a reminder. The universe might not play by the rules we've written for it. Imagine the quietest room in the universe, a space completely empty, stripped of all matter, radiation, even stray atoms. By all appearances, it should be nothingness incarnate. Yet quantum mechanics paints a far wilder picture. What we call a vacuum isn't empty at all. It's a seething, bubbling froth of virtual particles popping in and out of existence, a subatomic dance so energetic that its predicted power could tear the cosmos apart. Here's the catch: when we calculate this vacuum energy, the numbers are catastrophically wrong. Not by a little, by a factor of 10 followed by 120 zeros. This isn't just a rounding error. It's the greatest mismatch between theory and observation in all of science, a glaring blind spot known as the Vacuum Catastrophe. Let's break down the madness. According to quantum field theory, empty space is anything but empty. Particle-antiparticle pairs constantly flicker into being, borrowing energy from the vacuum before vanishing again in a time span so short it defies measurement. These quantum fluctuations aren't just mathematical quirks. They've been detected in labs through effects like the Casimir force, where two metal plates placed microscopically close in a vacuum feel a subtle push from the particles winking into existence around them. If you could tap into this energy, you'd have a power source beyond imagination. But here's where the math goes off the rails. When physicists sum up all these fleeting fluctuations to estimate the vacuum's energy density, the result is a number so enormous it would warp space-time beyond recognition. The universe should have ripped itself apart moments after the Big Bang, or at the very least, accelerated expansion so violently that galaxies never formed. Yet when we measure the actual energy of empty space, what cosmologists call dark energy, it's almost laughably tiny. Not 0, but 10 to the power of 120 times smaller than predicted. It's like calculating the weight of an ocean and getting a result lighter than a single raindrop. So what's going on? One possibility is that we're missing a crucial cancellation mechanism, some symmetry or unknown physics that neatly erases almost all vacuum energy, leaving behind the faint residue we observe. Supersymmetry, a popular but still unproven theory, suggests every particle has a superpartner that could balance the quantum scales. But even if sussy particles exist, they'd only reduce the discrepancy by half. Another idea is that multiple universes exist with random vacuum energies, and we just happen to live in the one where the numbers allow galaxies and life to exist. It's the ultimate anthropic cop-out, but the numbers are so extreme, some argue it's the only viable explanation. Then there's the radical notion that we're measuring the wrong thing entirely. Maybe vacuum energy isn't constant but evolves over time, or perhaps gravity interacts with quantum fields in ways we haven't yet imagined. String theorists propose extra dimensions could soak up the excess energy like a cosmic sponge, while others wonder if the vacuum itself is an illusion, a holographic projection from a deeper reality where energy balances differently. The vacuum catastrophe isn't just an academic curiosity, it's a fracture line running through modern physics. Solve it, and we might unlock quantum gravity or finally reconcile relativity with the subatomic world. Until then, the universe keeps whispering its most persistent riddle. Why does nothing weigh so much less than it should? The universe is expanding, that much we know for certain. But ask astronomers how fast, and you'll spark a debate that's been simmering for over a decade. On one side, we have the cosmic microwave background, the afterglow of the Big Bang, whispering that the universe's expansion rate, the Hubble constant, is about 67 kilometers per second per megaparsec. On the other, measurements of nearby supernova and pulsating stars insist it's closer to 73. That gap might seem small, but in cosmology, it's a chasm. Statistically, the odds of this discrepancy being a fluke are less than 1 in a million. Welcome to the Hubble Tension, a cosmic tug of war that could upend our understanding of everything from dark energy to the very fabric of space-time. So why can't we agree on the universe's speedometer? One possibility is that our tools are flawed. The CMB method looks back to the universe's infancy, extrapolating today's expansion from primordial ripples. Local measurements, meanwhile, rely on standard candles like Cepheid variable stars, whose predictable brightness lets us gauge distances. But what if Cepheids aren't as reliable as we thought? Or what if interstellar dust is subtly dimming their light, skewing the math? Teams have checked, rechecked, and invented new methods like using gravitational lensing or merging neutron stars, yet the tension persists. The more we refine our measurements, the more stubborn the gap becomes. That's when things get interesting. If the error isn't in our instruments, it might be in our theories. Maybe dark energy, the force accelerating cosmic expansion, isn't constant after all. Imagine it's a dial that's been slowly turning, growing stronger or weaker over time. That could explain why early universe probes and modern observations don't align. Alternatively, there might be an undiscovered particle, a dark radiation, that zipped through the cosmos in its youth, subtly altering the expansion rate we infer from the CMB. Then there's the nuclear option. What if general relativity, our gold standard for gravity, breaks down on cosmic scales? Modified gravity theories like Big Brother tweak Einstein's equations to fit the data without invoking dark energy. But these ideas come with their own headaches, often failing elsewhere while patching the Hubble gap. The stakes couldn't be higher. If the tension points to new physics, it might reveal a universe far stranger than we imagined, one where dark energy morphs over time, where invisible particles dance in the background, or where gravity itself wears a different face in different eras. Or perhaps, like the pioneer anomaly, the answer will be something humbler, a systematic error hiding in plain sight. For now, the Hubble tension stands as a cosmic wake-up call, reminding us that even the most trusted numbers in science are open to question, and that the universe still holds cards it hasn't shown us yet. Out of the silent blackness of space comes a signal so powerful it outshines entire galaxies for just a millisecond. Fast radio bursts are the universe's most enigmatic flashes, cosmic Morse code with no clear sender. First discovered in 2007, these bursts pack the energy of 500 suns into a blink so brief, if you sneeze, you'd miss it. Yet their brevity isn't the puzzle, it's their patterns. Some arrive randomly, like static from a broken radio. Others repeat with clockwork precision, ticking across the cosmos like a metronome set by an unseen hand. And when astronomers trace their origins, the bursts point to galaxies billions of light years away, far beyond the Milky Way's borders. So what could possibly produce such violent, fleeting signals? The leading suspect, magnetars neutron stars with magnetic fields so intense they could strip the data from a credit card halfway across the solar system. Picture a stellar corpse spinning furiously, its crust cracking under magnetic strain, releasing quakes that ripple through space as bursts of radio energy. It's a compelling theory, especially after a magnetar in our own galaxy emitted an FRB-like signal in 2020. But here's the snag: most repeating bursts don't match magnetar behavior. Their cadence is too regular, their energy too finely tuned, like a cosmic drummer keeping perfect time. That's where the plot thickens. Some bursts exhibit downward drifting, a hallmark of signals passing through turbulent plasma, suggesting they've traveled through the heart of distant galaxies. Others arrive with a twist, their radio waves polarized as if twisted by powerful magnetic fields. Then there's FRB 2021-20128A, a burst so intense it temporarily blinded telescopes, emitting more energy in a millisecond than our sun does in weeks. Natural explanations strain to account for such extremes, leaving room for wilder possibilities. Could these be alien beacons? The idea isn't as far-fetched as it sounds. A civilization advanced enough might use focused radio beams to propel interstellar sails, with leakage appearing as FRBs to distant observers. Or perhaps they're cosmic lighthouses, navigation pulses for ships crossing the void. Even SETI scientists take the hypothesis seriously, though no burst has ever carried the hallmarks of artificial encoding. Then there's the middle ground, exotic physics we've yet to imagine. Colliding neutron stars might create shockwaves that emit FRBs like cosmic thunderclaps, or blitzars, theoretical stars so dense they collapse directly into black holes, shedding their magnetic skins in one final, brilliant scream. Some theorists even speculate about cosmic strings defects in spacetime, left over from the Big Bang vibrating like guitar strings to produce these fleeting notes. Every new detection adds layers to the mystery. In 2022, astronomers caught an FRB from a globular cluster, a place where stars are packed so tightly, magnetars shouldn't form. Another burst traced to a galaxy with no active star formation, defying expectations that FRBs need young, chaotic environments. And then there's the WTF signal, not its official name, but fitting, a burst that seemed to carry a repeating structure, sparking brief but intense speculation about intelligence before natural explanations resurfaced. What makes FRBs so tantalizing isn't just their origin, but what they reveal along the way. As these signals traverse the cosmos, they interact with the sparse atoms between galaxies, allowing astronomers to weigh the universe's missing matter, the invisible web thought to hold galaxies together. Each burst is a flashlight beam cutting through cosmic fog, illuminating the dark corners we can't otherwise see. So are they magnetars, aliens, or something entirely new? The answer might reshape our understanding of the universe's most extreme environments, or reveal that we're not the only ones listening to the stars. Until then, every millisecond burst is a postcard from the unknown, waiting to be decoded. Hidden behind the curtain of our own Milky Way, where starlight dims into a haze of cosmic dust, something colossal is pulling at us with the force of 1,000,000 billion suns. Astronomers call it the Great Attractor, a gravitational anomaly so powerful that it's dragging not just our galaxy, but thousands of others toward it at over 600 kilometers per second. Think of it as a cosmic riptide, invisible from Earth's vantage point, yet bending the paths of entire galaxy clusters like leaves caught in a river's current. But here's the catch: we can't see what's doing the pulling. The Milky Way's dusty disk blocks our view, leaving us to piece together the puzzle through indirect clues and the frantic motion of galaxies caught in its grip. The first hints emerged in the 1970s, when astronomers noticed something odd about the cosmic microwave background, the afterglow of the Big Bang. It wasn't perfectly uniform. One hemisphere appeared slightly warmer, as if we were moving through space at breakneck speed. Follow-up observations confirmed it. Our local group of galaxies, including Andromeda and the Milky Way, was racing toward a mysterious point in the constellation Centaurus. At first, scientists assumed it was the Shapley supercluster, a dense knot of galaxies about 650 million light-years away, but the math didn't add up. Shapley's gravity couldn't fully explain the sheer momentum of our motion. There had to be something else, something hidden. Enter the Great Attractor. Current estimates suggest it's a staggering 400 million light-years away, with a mass of tens of thousands of Milky Ways packed into a region of space smaller than most superclusters. Infrared and radio telescopes capable of peering through the Milky Way's dust have glimpsed hints of its structure, a sprawling confluence of galaxy clusters, each adding to the gravitational tug. Yet even this might not be the full story. Some researchers propose the attractor is just the tip of the iceberg, a signpost pointing to an even larger structure, like the Vela supercluster or the mysterious dipole repeller, a vast void whose emptiness pushes galaxies away like a cosmic exhale. Then there's the unsettling possibility that the Great Attractor isn't just a cluster of galaxies. Could it be a concentration of dark matter so dense it warps spacetime like a hidden whirlpool? Or a relic of primordial fluctuations from the Big Bang, a fossilized ripple frozen in the fabric of the cosmos? The wildest theories even flirt with the idea of a massive compact halo object, a hypothetical monster like a primordial black hole left over from the universe's birth, lurking unseen in the interstellar shadows. What's at stake isn't just the fate of our galactic neighborhood. The Great Attractor challenges our understanding of cosmic flow, the grand choreography of galaxies dancing to gravity's tune. If its pull defies predictions, it might mean our models of large-scale structure are missing a crucial ingredient, like an unknown form of dark energy or a flaw in how we measure distances across the void. Every new map of galaxy motions, every deeper peek through the dust, brings us closer to unraveling the mystery. For now, the Great Attractor remains a cosmic siren calling us toward the unknown. It's a reminder that even as we chart the universe, some of its most powerful forces are still just whispers in the dark, waiting to be heard. On a quiet August night in 1977, a radio telescope in Ohio picked up something extraordinary, a burst of noise so strong, so peculiar, that it stood out against the cosmic background like a scream in a silent room. Lasting exactly 72 seconds, the signal blazed at a frequency near 1420 MHz, the exact wavelength scientists had predicted an alien civilization might use to broadcast its presence. When astronomer Jerry Amon saw the data printout, he circled the anomaly in red ink and scribbled a single word beside it: "Wow." That moment birthed one of astronomy's greatest unsolved mysteries, the Wow Signal, a fleeting radio whisper that vanished as suddenly as it appeared, leaving behind no repeats, no explanations, and a question that still haunts us. Was this our first brush with an alien hello? What made the signal so tantalizing wasn't just its strength, 30 times louder than the ambient noise of space, but its narrow frequency range. Natural cosmic phenomena, like pulsars or quasars, usually broadcast across a wide spectrum, like static on a radio dial. The Wow signal, by contrast, was a laser-sharp spike, the kind you'd expect from a focused transmitter. Even more intriguing was its behavior. The telescope's design, which used two feed horns to scan the sky, meant the signal peaked in one horn, then faded as the other took over. Exactly what you'd see if it originated from deep space rather than earthly interference. Yet despite decades of follow-up scans, including targeted searches by the Very Large Array, the signal never returned. It was a cosmic one-hit wonder, here and gone without a trace. So what could it have been? Skeptics point to more mundane explanations. A passing comet, like 266P/Christensen, was once proposed as the culprit, its hydrogen cloud emitting a burst at the right frequency. But the timing and location didn't quite match. Others suggest it might have been a secret military satellite or a rogue transmission bouncing off space debris, though no records corroborate such an event. Then there's the wild card, a glitch in the telescope itself, an electronic hiccup mimicking an artificial signal. But the Big Ear telescope was meticulously calibrated, and no malfunction was ever found. The absence of a repeat is the real head-scratcher. If aliens were deliberately signaling us, why just once? One theory posits it could have been a targeted beacon, sweeping across our solar system like a lighthouse beam, briefly illuminating Earth before moving on. Or perhaps it was an accidental leak, an alien equivalent of our own early TV broadcasts, radiating into the void before they learned to shield their transmissions. The truth might be even stranger. Some researchers speculate the signal could have been a cosmic mirror effect, where interstellar plasma bent and amplified a distant natural source, creating a temporary flare visible only to us. The Wow signal's legacy isn't just about aliens, it's a lesson in humility. For all our technology, the universe still throws curveballs we can't explain. It reminds us that the search for extraterrestrial intelligence isn't just about antennas and algorithms. It's about patience, persistence, and the willingness to sit with uncertainty. Because somewhere out there, in the vast radio silence of space, another Wow might be waiting, and next time we'll be ready to listen. In October 2017, astronomers spotted something extraordinary, a visitor from another star system hurtling through our cosmic backyard. Named Oumuamua, Hawaiian for scout, this interstellar interloper defied all expectations. Unlike any comet or asteroid we'd seen before, it was shaped like a cosmic cigar, roughly 400 meters long but only 40 meters wide, tumbling end over end through space. But the real shock came when telescopes tracked its departure. Instead of slowing down as expected under the sun's gravity, Oumuamua sped up, as if pushed by some unseen force. The discovery sent shockwaves through the scientific community, sparking a debate that continues to this day. Were we looking at a bizarre natural object, or something far more extraordinary? Mainstream science leans toward exotic but natural explanations. One leading theory suggests Oumuamua was a fragment of a Pluto-like world, sheared off by a distant collision and rich in frozen nitrogen. As it approached the sun, the intense heat could have vaporized this nitrogen ice, creating a propulsive jet that acted like a natural thruster. No outgassing visible to our telescopes, but enough to nudge it faster. Others propose it might be a cosmic dust bunny, an ultra-low-density aggregate of interstellar debris so light that even sunlight could push it along. Then there's the hydrogen iceberg hypothesis, a chunk of frozen hydrogen slowly boiling away in sunlight, leaving no dusty trail for us to detect. But for all these theories, puzzling gaps remain. Why did Oumuamua accelerate so smoothly without the erratic bursts typical of cometary outgassing? How did it maintain such an unusually elongated shape after billions of years of cosmic wear and tear? The lack of a visible coma or tail hallmarks of icy bodies shedding material only deepened the mystery. These anomalies led some, like Harvard astrophysicist Avi Loeb, to suggest a more radical possibility. Oumuamua could have been artificial in origin. Perhaps a light sail propelled by starlight pressure, or even a derelict probe from a long-vanished civilization. The idea isn't as far-fetched as it sounds. Humanity's own light-powered spacecraft, like the Breakthrough Starshot project, rely on similar technology. Critics counter that extraordinary claims require extraordinary evidence, and Oumuamua's quirks, while unusual, don't definitively point to aliens. The object's faint reflectivity and reddish hue align with known space rocks, and its tumbling motion suggests a natural origin. Moreover, the statistical likelihood of stumbling upon alien tech versus a rare but natural cosmic vagabond leans heavily toward the latter. Yet the debate persists precisely because Oumuamua defies easy categorization, a Rorschach test for how we interpret cosmic anomalies. What makes Oumuamua so compelling isn't just its identity crisis, but what it represents: proof that interstellar visitors are real and more are likely on the way. Since its discovery, astronomers have spotted other interstellar objects like the comet Borisov, which behaved far more predictably. With upcoming telescopes like the Vera Rubin Observatory set to scan the skies with unprecedented precision, we may soon find dozens more of these cosmic nomads, each potentially stranger than the last. Whether Oumuamua was a nitrogen iceberg, a hydrogen snowball, or something even more exotic, its fleeting passage through our solar system left an indelible mark. It challenged our assumptions, sharpened our tools, and reminded us that the universe is always capable of surprises. The next time an interstellar visitor arrives, we'll be ready not just to watch it pass, but to chase it down, probe its secrets, and finally answer the question: are we alone or just late to a conversation that's been going on for billions of years? Black holes are nature's ultimate vaults, cosmic locks that swallow everything, even light, without a trace. But here's the paradox: quantum mechanics insists that information, the blueprint of every particle and force, can never truly vanish. It might get scrambled, hidden, or rearranged, but it must persist. Yet black holes, with their crushing singularities and inescapable event horizons, seem to erase information entirely. This contradiction, the black hole information paradox, has divided physicists for decades, pitting the unshakable laws of quantum theory against Einstein's vision of gravity. And at the heart of the storm, Stephen Hawking's bombshell discovery that black holes aren't so black after all. Hawking radiation changed everything. In the 1970s, he calculated that black holes slowly leak energy, emitting faint particles until they eventually evaporate. But here's the catch: this radiation appeared random, devoid of any fingerprints from the material that originally fell in. Imagine burning an encyclopedia and claiming the rising smoke carries no trace of the words it once held. That's the crisis. If Hawking was right, information was being permanently destroyed, violating quantum mechanics' core tenet. The scientific world split into warring camps. Some, like Hawking himself, initially argued that information truly was lost, a heresy that sparked pushback from giants like Leonard Susskind, who declared, If quantum mechanics is wrong, we might as well throw out all of modern physics. Enter the holographic principle, a radical idea that rewrites the rules of reality. Picture a black hole's event horizon not as a one-way membrane, but as a pixelated screen, encoding all the information of whatever falls inside onto its two-dimensional surface. It's like storing a 3D movie on a flat DVD, every detail preserved, just rewritten in a new language. In this view, the universe itself might be a hologram with the information of everything we see, touch, and feel projected from some distant, lower dimensional boundary. If true, black holes don't destroy information, they just translate it into a form we can't yet decode. Then there's the firewall paradox, a cosmic horror lurking at the event horizon. To preserve information, some theorists suggest that the boundary isn't the gentle gateway relativity predicts, but a searing wall of high-energy particles that incinerates anything crossing it. This firewall would scramble information into Hawking radiation, saving quantum mechanics but violating Einstein's principle that free-falling observers should notice nothing unusual as they pass the point of no return. It's a cosmic catch-22, either information vanishes, relativity breaks, or quantum mechanics is incomplete. The stakes couldn't be higher. If information can be lost, causality itself unravels, predictions become impossible, and the past could rewrite itself. But if it's preserved in some exotic form, we might be on the verge of discovering a deeper layer of reality, where space-time and quantum entanglement are two sides of the same coin. Recent breakthroughs like the detection of soft hair, low-energy quantum imprints on black holes hint at possible solutions, while experiments with quantum computers simulate how information might escape. For now, the paradox stands as a beacon at the frontier of physics, challenging us to reconcile the quantum and cosmic realms. Whether the answer lies in holograms, firewalls, or something stranger, one thing is clear: black holes aren't just swallowing matter, they're forcing us to rethink the very nature of existence. Einstein called it spooky action at a distance, a phrase that perfectly captures the unnerving heart of the EPR paradox, a thought experiment so unsettling it made the father of relativity himself question whether quantum mechanics could possibly be complete. Picture two particles born together, their properties entangled like cosmic twins. Measure one's spin as up, and instantly, no matter how far apart they've drifted, the other snaps to down. No signal passes between them, no force connects them, yet they coordinate faster than light could ever bridge the gap. To Einstein, this was impossible, a violation of relativity's sacred speed limit. But here's the twist: decades of experiments have proven this spookiness is real, and it's now the beating heart of technologies like quantum encryption. How does this apparent faster-than-light conversation work, and what does it reveal about the fabric of reality? The EPR paradox takes its name from Einstein and his colleagues Boris Podolsky and Nathan Rosen, who devised it in 1935 as a challenge to quantum theory's completeness. Their argument was elegant. If quantum mechanics allowed entangled particles to influence each other instantly across vast distances, it either meant the theory was flawed, missing hidden variables that predetermined particle states, or that information was traveling faster than light, which relativity forbade. Einstein favored the hidden variables explanation, believing the universe couldn't possibly operate on such spooky randomness. But quantum pioneers like Niels Bohr disagreed, insisting the particles existed in a fuzzy superposition until measured, with no hidden hand guiding them. The breakthrough came in 1964 with physicist John Bell's theorem, a mathematical framework to test whether hidden variables could explain entanglement. Bell calculated that if hidden variables existed, entangled particles would correlate only up to a certain limit. Quantum mechanics, however, predicted stronger correlations, ones that couldn't be explained by any local, predetermined properties. When experiments like Alain aspects in the 1980s confirmed these stronger correlations, the verdict was clear: Einstein's hidden variables didn't exist. Entanglement's spookiness was real, but here's where things get truly strange. This instantaneous coordination doesn't actually transmit information faster than light. While measuring one particle instantly affects its partner, the outcome is always random. You can't control what spin or polarization you'll get, so you can't encode a message. It's like having two synchronized coin flips. One person's heads ensures the other's tails, but neither can choose the result. This subtle distinction preserves relativity's speed limit while still allowing quantum systems to behave in ways that seem to defy classical intuition. Today, this paradox isn't just philosophy, it's the engine behind quantum technologies. Quantum computers leverage entanglement to perform calculations at speeds impossible for classical machines, while quantum cryptography uses it to create unhackable communication channels. The very phenomenon Einstein dismissed as impossible now promises to revolutionize everything from drug discovery to cybersecurity. Yet the deepest question remains unanswered: how do entangled particles know each other's states? Some theories suggest the universe is fundamentally non-local, with particles connected through a deeper layer of reality where distance is meaningless. Others propose that entanglement reveals a holographic universe, where what we perceive as separation is just an illusion. Whatever the answer, the EPR paradox stands as a monument to quantum mechanics' enduring mystery, a reminder that the universe is far stranger than even Einstein dared to imagine. What if everything you know, your memories, the world around you, even the laws of physics, were just a fleeting glitch in an endless sea of chaos? That's the nightmare scenario posed by the Boltzmann brain, a thought experiment so unsettling it turns our understanding of reality inside out. Named after physicist Ludwig Boltzmann, who grappled with how order emerges from disorder, the idea goes like this: in an infinite universe where entropy reigns supreme, random fluctuations could, by sheer chance, assemble a fully formed, self-aware mind complete with false memories of a past that never existed. Not just once, but countless times over eternity. And statistically, these phantom consciousnesses would vastly outnumber real, biologically evolved beings like us. So how do you prove you're not one of them? The paradox emerges from thermodynamics' second law, which states that systems tend toward disorder over time. But Boltzmann realized that in an infinite timeline, even the most improbable events, like all the air in a room suddenly gathering in one corner, must occasionally happen. Extend this to consciousness, and the implications are staggering. If the universe lasts long enough, thermal fluctuations could spontaneously conjure a brain, complete with fabricated sensory input, convinced it's living a coherent life. It might remember drinking coffee this morning, feel the warmth of sunlight, even ponder the nature of existence, all while floating utterly alone in the void. Critics argue this is philosophy masquerading as physics, but the math is chillingly sound. In a truly eternal cosmos, Boltzmann brains aren't just possible, they're inevitable. Modern cosmology amplifies the dread. If dark energy keeps accelerating the universe's expansion, eventually all matter will be so scattered that only these phantom minds flicker briefly in the darkness, their lives lasting mere seconds before dissolving back into chaos. The ultimate cosmic irony: the longer the universe exists, the more likely it is that you're a Boltzmann brain right now, hallucinating this very sentence. Yet the theory isn't without escape routes. Some physicists propose that our universe's low entropy starting point, the Big Bang's inexplicable order, makes Boltzmann brains statistically unlikely. Others suggest the multiverse could dilute their probability, with countless stable universes like ours outweighing the blips of false consciousness. Then there's the simplest rebuttal. If we were Boltzmann brains, our experiences would likely be fragmented and illogical, not the consistent, law-bound reality we observe. But the deepest question lingers: does the universe favor complexity, or is it fundamentally a machine for generating chaos? The Boltzmann brain forces us to confront whether our thirst for meaning is just a byproduct of randomness or evidence of something deeper. For now, it remains the ultimate existential riddle, a whisper from the void asking us to trust our own minds, and that's a leap of faith even physics can't quantify. What if everything around you, the stars, the laws of physics, even the sensation of wind on your skin, was nothing more than lines of code in an unfathomably advanced simulation? The simulation hypothesis isn't just sci-fi fodder. It's a legitimate philosophical and scientific debate that stretches from ancient Greek allegories to Silicon Valley boardrooms. Plato's cave suggested reality might be shadows on a wall. Descartes wondered if an evil demon deceived our senses. Today, figures like Elon Musk argue the odds we're in base reality are astronomically low, billions to one. But what would it take to prove the universe runs on cosmic ones and zeros? Start with the glitches. Every programmer knows no code is perfect, tiny errors creep in. If we're living in a simulation, perhaps the universe has its own bugs. Some physicists search for pixelation in the fabric of space-time, minute inconsistencies in energy levels or quantum behavior that hint at underlying computational limits. Others look for cheats, shortcuts a simulation might take to conserve processing power. For instance, quantum mechanics' uncertainty principle could be a rendering trick. Particles only load their properties when observed, like a video game optimizing graphics only where players look. Even the speed of light might be nothing more than a processor speed limit, capping how fast information can travel to prevent system overload. Then there's the math itself. The universe runs on mathematical laws so precise they feel engineered. From the golden ratio in sunflowers to the gravitational constant fine-tuned to allow stars and planets, reality seems suspiciously well-designed. Nobel laureate George Smoot once quipped that the cosmos' orderliness points to a universe that looks like a thought. Some theorists take this further, suggesting advanced civilizations might encode their ancestors' histories as simulations, making it statistically probable we're in one of countless iterations rather than the original. But how could we test this? One approach involves probing the universe's resolution. Just as a digital image breaks down into pixels under magnification, space-time might reveal granularity at the Planck scale, distances so tiny they're indivisible. Experiments with high-energy particle collisions or quantum gravity detectors could uncover this grid-like structure. Another tactic: search for overrides. If the simulation has a creator, they might intervene, leaving traces like unnatural energy fluctuations or mathematical anomalies in cosmic background data. Critics counter that the hypothesis is unfalsifiable, a clever thought experiment with no exit strategy. Even if we found evidence, how would we know it wasn't planted by the simulators? And then there's Occam's razor. Why invent godlike programmers when physics explains reality well enough? Yet the debate persists because it forces us to confront the nature of existence itself. Whether we're in a simulation or not, the question reshapes how we view consciousness, free will, and the boundaries of science. So where does that leave us? Maybe the answer doesn't matter. If the simulation is flawless, it's indistinguishable from reality, making our experiences no less meaningful. Or perhaps the truth is stranger still, that the universe is both real and simulated, a layered puzzle where every discovery peels back another veil. Until then, the hypothesis remains the ultimate cosmic mirror, reflecting our deepest questions back at us, not just about the universe's nature, but our place within it. Imagine firing tiny particles, electrons or photons, one by one at a barrier with two slits. Logic says each particle should pass through one slit or the other, leaving two distinct clusters on the detector screen behind it. But that's not what happens. Instead, over time, an interference pattern emerges, a series of light and dark bands, as if the particles behaved like waves, crashing into each other like ripples in a pond. Now here's where things get weird. The moment you place a detector to observe which slit each particle actually goes through, the interference pattern vanishes. The particles suddenly choose to act like discrete objects, leaving two simple bands behind. It's as if the universe is playing a game of hide and seek, changing its behavior the instant you try to peek. This is the double slit experiment, and it's the heart of the quantum measurement problem, one of the most profound mysteries in physics. Why does observation seem to rewrite reality? One interpretation, the Copenhagen view, suggests that particles exist in a superposition, a blur of all possible states, until measurement forces them to collapse into a single outcome. In this framework, the act of observation isn't passive. It's transformative, like a camera flash freezing a spinning fan into a single blade position. But this raises a thorny question. What counts as an observer? Does it require a conscious human, or would a machine suffice? Some, like physicist John von Neumann, argued that consciousness itself might be the trigger, implying a universe where mind and matter are inextricably linked. This idea, though poetic, makes many scientists uneasy. It feels too much like philosophy trespassing into physics. Enter the many worlds interpretation, a radical alternative. Here, there's no collapse at all. Instead, every possible outcome branches into a new, parallel universe. In one world, the particle goes through the left slit, in another, the right. The interference pattern isn't destroyed, it's just spread across dimensions we can't access. This sidesteps the observer problem but leaves us with an infinite, ever-splitting multiverse, a concept so extravagant it strains credulity. Then there's objective collapse theories, which propose that wave functions collapse spontaneously due to some yet undiscovered physical mechanism, not observation. Gravity, for instance, might destabilize superpositions at a certain scale, explaining why large objects don't blur into quantum fuzz. Experiments with nanoscale diamonds and vibrating cantilevers are testing this idea, searching for the exact tipping point where quantum weirdness gives way to classical certainty. The stakes are more than philosophical. Quantum computers rely on maintaining superpositions. If consciousness or some other external factor disrupts them, it could limit their potential. Meanwhile, interpretations like cubism treat quantum states as personal beliefs, updating not because reality changes, but because our knowledge does. It's a statistical tool, not a window into the universe's soul. At its core, the measurement problem forces us to confront a humbling truth. Reality might not play by rules we can neatly separate from our attempts to understand it. Whether it's conscious observers, branching timelines, or hidden physics, the answer will redefine not just quantum theory, but our very notion of what it means to be real. Until then, every observation is a reminder we're not just studying the universe, we're inescapably part of the experiment. The universe has a glaring accounting error, one so profound it makes our very existence possible. According to the laws of physics, the Big Bang should have created matter and antimatter in perfect, symmetrical balance. Every proton born would have been matched by an antiproton, every electron by a positron, all destined to annihilate each other in bursts of pure energy. And yet, here we are. The stars, planets, and even the device you're watching this on are built from matter, with antimatter seemingly vanished into thin air. This cosmic imbalance, known as Baryon asymmetry, is one of the universe's greatest unsolved puzzles, a 1 in a billion fluke that shouldn't have happened, but did. So where did all the antimatter go? Our first clue comes from something called CP violation, a subtle quirk in how particles and antiparticles behave. Normally, the universe should treat matter and antimatter with equal indifference, obeying a principle called charge parity symmetry. But in 1964, physicists James Cronin and Val Fitch discovered that certain particles, like neutral kaons, decay slightly differently than their antimatter counterparts. It's as if the cosmos has a tiny, built-in preference for matter, a bias so small it's like flipping a coin that lands heads 51 times out of 100. Over billions of years, that minuscule preference could have tipped the scales, allowing matter to dominate. But here's the problem. CP violation in known particles is far too weak to explain the overwhelming matter surplus we see today. That's where leptogenesis enters the picture. This theory suggests that in the universe's earliest moments, ultra-heavy neutrinos, particles far more massive than any we've detected, decayed unevenly, producing more matter than antimatter. These decays could have seeded the cosmos with an excess of leptons, which then converted into baryons through processes we're still unraveling. It's a cosmic domino effect, where tiny asymmetries in one family of particles ripple outward to shape everything we see. Experiments like the Deep Underground Neutrino Experiment are hunting for clues, probing neutrino behavior for hints of this PRIMORDIAL Chinese letter. Meanwhile, particle colliders are recreating the conditions of the early universe, smashing atoms together to see if antimatter behaves differently in ways we've missed. The LHCb experiment at CERN has spotted tantalizing CP violations in beauty quarks, but the numbers still don't add up. Some theorists speculate that antimatter might not have vanished at all. It could be hiding in vast, invisible, anti-galaxies, lurking beyond the observable universe. Others wonder if antimatter has a tiny gravitational repulsion, causing it to flee into cosmic voids. The stakes couldn't be higher. Solve this riddle, and we might finally understand why the universe didn't annihilate itself moments after birth, and whether life's existence hinges on a single, fragile imbalance. For now, every atom in your body is a relic of that ancient victory, a reminder that the cosmos played favorites just enough to let us be here to wonder why. Gravity is the universe's shyest force, so feeble that a simple fridge magnet can defy the entire Earth's pull on a paperclip. Yet gravity's weakness isn't just a curiosity, it's a glaring inconsistency in the fabric of physics. The other fundamental force is electromagnetism, the strong nuclear force that glues atoms together, and the weak force behind radioactive decay outmuscle gravity by factors of trillions. A single proton's electric repulsion can overpower the gravitational attraction of an entire planet. This bizarre imbalance is the hierarchy problem, a riddle that keeps physicists awake at night. Why is gravity so vanishingly weak compared to everything else? One tantalizing clue might lie in the geometry of reality itself. Imagine ants crawling across a bedsheet. To them, the sheet is their entire world, until you roll it up into a tube. Suddenly, a dimension they never perceived exists, hidden in plain sight. This is the essence of extra-dimensional theories, like the brain world scenario. If gravity, unlike other forces, can leak into higher dimensions we can't see, its apparent weakness in our four-dimensional space-time might just be an illusion. Picture a hose spraying water in 3 dimensions. From far away, the stream seems weak, but up close, you realize most of its strength was spreading into unseen directions. If gravity operates similarly, its true power could be diluted across dimensions beyond our perception. Experiments at the Large Hadron Collider hunt for evidence of these hidden realms by searching for missing energy particles that might briefly vanish into higher dimensions before snapping back into ours. Then there's supersymmetry, an elegant but unproven theory that posits every known particle has a heavier superpartner. These shadow particles could balance the quantum scales, cancelling out extreme values in equations that currently make gravity's feebleness seem arbitrary. If supersymmetric particles exist, they'd not only tidy up the hierarchy problem but also explain dark matter. The catch, after decades of searching, the LHC has yet to find a single superpartner. Some physicists argue we might need higher energies to spot them. Others wonder if supersymmetry isn't the universe's answer after all. But what if the problem runs deeper? Quantum field theory treats gravity differently than other forces, refusing to play nice with the rules governing particles like electrons or quarks. This tension suggests gravity might not be a force in the traditional sense but a side effect of spacetime's curvature, as Einstein proposed. If true, the hierarchy problem isn't about strength but about categorization. We're comparing apples to cosmic oranges. String theory attempts to bridge this divide, weaving all forces into vibrations of tiny, multidimensional strings. Yet without experimental proof, these ideas remain beautiful speculation. The stakes are cosmic. Solve the hierarchy problem, and we might unlock quantum gravity, unite relativity with particle physics, or even discover that our universe is just one fragile bubble in a vast multiverse where gravity's strength varies wildly. For now, every falling apple, every orbiting planet, and every magnet stuck to your fridge is a reminder gravity's quiet weakness might be the universe's loudest unanswered question. Imagine hurtling through the void of space in a rocket accelerating so fiercely it pins you to your seat. To you, the vacuum outside appears silent and empty, but according to quantum physics, your motion would transform that nothingness into a swirling storm of heat and light. This is the Unruh Effect, a mind-bending prediction where acceleration conjures particles from pure emptiness, revealing a universe where reality itself depends on how fast you're pushing the gas pedal. The effect takes its name from physicist William Unruh, who in 1976 realized something astonishing. An observer accelerating through a vacuum would perceive warmth where an inertial observer sees only cold, dead space. It's not an illusion. The accelerating detector would genuinely experience a bath of thermal radiation, as real to it as sunlight feels to us. The math mirrors Hawking radiation, where black holes leak energy from their event horizons, but here the heat emerges purely from motion. Picture a spaceship with its engines locked at full throttle. As it approaches near light speeds, the crew might witness virtual particles, usually fleeting quantum fluctuations, materializing into detectable warmth, like static resolving into a roaring fire the faster they go. What makes this so counterintuitive is that quantum field theory treats particles not as fixed objects, but as excitations in underlying fields. In flat spacetime, two observers moving at constant velocity agree on what counts as a particle. But introduce acceleration and their realities diverge violently. The inertial observer sees empty space. The accelerating one encounters a thermal fog of particles with a temperature proportional to their acceleration. For a human astronaut, the effect would be imperceptibly faint. You'd need accelerations trillions of times stronger than Earth's gravity to notice even a whisper of warmth. But theoretically, it's inescapable. Motion itself warps the quantum vacuum into something tangible. the Unruh Effect isn't just a curiosity, it's a stress test for physics' most cherished principles. It forces quantum mechanics and relativity into a head-on collision, exposing cracks in how we define fundamental concepts like particles and vacuum. If reality looks different depending on your motion, does that mean particles are less objective than we thought? Some interpretations suggest yes, that particles are like words in a language, meaningful only relative to the observer's state. Others argue the effect underscores the reality of quantum fields over particles, with detection events being secondary to the deeper, invariant fields beneath. Experiments to confirm the Unruh effect directly remain fantastically difficult, but clever workarounds exist. Analog systems using superfluid helium or Bose-Einstein condensates simulate the conditions, while observations of electrons spiraling in intense magnetic fields hint at analogous radiation. Meanwhile, the effect's kinship to Hawking radiation offers indirect support. If black holes glow, why not accelerating rockets? At its core, the Unruh effect blurs the line between motion and heat, between nothingness and something. It whispers that the universe is far more restless than it appears, and that even in the deepest vacuum there's no true stillness, only a silence waiting to be shattered by the right kind of movement. What if everything you see, touch, and experience, every star, every atom, even the fabric of spacetime itself, is nothing more than a shimmering illusion, a cosmic mirage projected from the edges of reality? This is the audacious claim of the holographic principle, a theory so radical it redefines the very nature of existence. Imagine the universe as a colossal hologram, where all the information needed to construct a three-dimensional world is secretly encoded on a two-dimensional surface at its boundary. Your morning coffee, the screen you're watching right now, even the neurons firing in your brain, all might just be shadows cast by data etched onto some distant, flat horizon. The idea traces back to black holes, those cosmic paradox factories. When matter falls into a black hole, classical physics says it's lost forever, but quantum mechanics insists the information must persist. In the 1990s, physicist Leonard Susskind and Nobel laureate Gerard T. Hooft proposed a solution. The information isn't destroyed, it's smeared across the black hole's event horizon like ink on a microscopic parchment. Stretch this logic to the entire cosmos, and you get the holographic principle, a universe where the true reality isn't the 3D space we inhabit, but a hidden 2D surface encoding it all. Think of it like a movie screen. The images appear three-dimensional, but they're really just patterns of light projected from flat pixels. Similarly, the holographic principle suggests that the particles, forces, and even gravity we perceive are pixels on a universal screen. The cosmic microwave background, the edge of the observable universe, or some other boundary we've yet to identify. This isn't just philosophy, the math checks out. Calculations in string theory and quantum gravity reveal that the information content of any space doesn't scale with its volume, but with its surface area, exactly what you'd expect if the universe were a hologram. But how could flatness create depth? The key lies in entanglement, the quantum phenomenon linking particles across space. These connections might stitch together the 2D data into the 3D world we perceive, like threads weaving a tapestry. Experiments with quantum computers have even simulated mini-holographic universes, where manipulating entangled qubits alters the space they encode, a tantalizing hint that the principle could be more than metaphor. The implications are staggering. If true, the holographic principle could finally reconcile Einstein's gravity with quantum mechanics, showing they're two sides of the same coin. It might explain why spacetime seems pixelated at the tiniest scales, or why black holes have entropy, a measure of information proportional to their surface area. Some theorists even speculate that time itself could emerge from this cosmic encoding, with our perception of its flow being an artifact of how the projection updates. Yet mysteries linger. If we're living in a hologram, what's the projector? Could the universe be a simulation running on some unfathomable hard drive? Or is this just how reality fundamentally operates? For now, the holographic principle remains a breathtaking hypothesis, one that turns the solid ground beneath our feet into a shimmering illusion, inviting us to question whether the cosmos is far stranger and far more interconnected than we ever dreamed. Black holes are the universe's ultimate vaults, their event horizons locking singularities away from prying eyes like cosmic prison bars. But what if those bars didn't exist? What if you could stumble upon a singularity floating bare in space, its infinite density exposed for all to see? This nightmare scenario is the heart of the cosmic censorship hypothesis, a daring conjecture that nature abhors naked singularities as much as a vacuum abhors uncovered leftovers. General relativity, in its raw mathematical form, absolutely permits these uncloaked monstrosities. Yet every singularity we've ever detected hides behind an event horizon's impenetrable veil. Is this a fundamental law of physics, or just a quirk of the equations waiting to be violated? The idea traces back to Roger Penrose, the Nobel-winning physicist who first proposed that the universe might enforce a kind of decency principle, a cosmic firewall preventing singularities from flashing their infinite curves at the cosmos. Think of it like nature's version of a blur filter, automatically pixelating anything too extreme for spacetime to handle. Without this censorship, the deterministic fabric of reality could unravel. Singularities aren't just ultra-dense objects. They're points where the laws of physics break down, where gravity becomes infinite and predictability goes out the window. An exposed singularity could spit out unpredictable energies, rewrite causality on a whim, or even spawn new universes like bubbles in a boiling pot. The cosmic censorship hypothesis is essentially physics' plea for sanity. Whatever happens inside the horizon stays inside the horizon, but proving this isn't so simple. While black holes with event horizons fit neatly into our models, mathematics also allows for naked singularities to form under special conditions, like if a black hole spins so fast it flings off its horizon, or if two ultra-compact objects collide in just the right way to birth a singularity without the usual protective shell. Supercomputer simulations have shown tantalizing glimpses of these scenarios, where the horizon briefly tears open like a curtain yanked aside, yet no observational evidence exists. Not a single X-ray flare or gravitational wave signature has ever betrayed the presence of a naked singularity out there in the wild. This absence fuels fierce debate. Some theorists argue that censorship isn't a law but an accident, a statistical inevitability because forming naked singularities requires impossibly precise conditions. Others see it as a clue to deeper physics, like quantum gravity stepping in to heal spacetime before singularities can strip bare. There's even a radical third option, that naked singularities do exist, but they're disguised as something else. Could certain pulsars or gamma-ray bursts actually be singularities in clever camouflage? The universe might be playing a shell game, hiding its most dangerous objects in plain sight. The stakes, if censorship fails our understanding of predictability, the bedrock of science itself, could collapse. Imagine throwing a baseball into a naked singularity and watching it re-emit as a flock of singing toasters, or worse, as a new set of physical laws. The cosmos would become a casino where the house rules change without warning. For now, the hypothesis stands as both a shield and a challenge, a reminder that some doors in the universe might be locked for a reason, and that behind them could lie wonders or terrors we're not yet equipped to face. Picture a cosmic kaleidoscope where every twist creates a new universe with its own unique set of physical laws, some where gravity is weaker, others where atoms never formed, and perhaps even a few where your morning coffee decided to defy gravity and float right out of the cup. This isn't just wild speculation. It's a direct consequence of inflationary theory, the leading explanation for the Big Bang's explosive beginnings. According to this framework, the universe didn't just expand, it underwent a hyperfast stretching, a fraction of a second after its birth, that could have seeded countless bubble universes, each with its own random quirks in the fundamental constants. But if these alternate realities exist, forever severed from our own by the unimaginable distances between them, how could we ever hope to catch a glimpse of them? The multiverse hypothesis isn't just about quantity, it's about variation. Tiny quantum fluctuations during inflation, magnified to cosmic scales, might have locked in different values for things like the strength of electromagnetism or the mass of electrons in each bubble. In some, stars might burn out in an instant. In others, matter could be so stable that life emerges in forms we can't even fathom. The real stunner: if the multiverse is infinite, there's a version of you out there who made every possible choice, from taking that job offer to inventing time travel, while another version never existed at all. But before you start pondering your alternate selves, here's the catch. These universes aren't just far away, they're fundamentally unreachable. The space between them expands faster than light could ever bridge, leaving us no way to send probes, signals, or even a cosmic postcard. So how do we test the untestable? Scientists have turned to clever, indirect methods. One approach involves hunting for bruises in our own universe, anomalies in the cosmic microwave background where a neighboring bubble universe might have bumped into ours long ago, leaving faint imprints like a dent in space-time. Another tactic leans on math. If the multiverse is real, the statistical distribution of physical constants in our universe should look like a winning lottery ticket amid a sea of losing ones. The fact that our laws seem improbably fine-tuned for life could be circumstantial evidence that we're just one lucky outcome in an infinite cosmic casino. Yet the multiverse remains controversial, with critics arguing it veers dangerously close to metaphysics. Without observable proof, how is it different from saying anything is possible somewhere? Even proponents admit the challenge. Nobel laureate David Gross famously called the idea a dangerous one that may not even be falsifiable. But defenders counter that skepticism once surrounded now confirmed ideas like black holes and the Big Bang itself. The search for validation continues in unexpected places, from quantum experiments simulating parallel realities to AI models mapping how alternate physics might play out. Perhaps the most tantalizing clue lies in the very fabric of reality. If the multiverse exists, quantum entanglement, those spooky connections between particles, might be the ghostly handshake between universes, a subtle hint that our cosmos isn't as isolated as it seems. Until then, the multiverse remains the ultimate thought experiment, a mirror held up to our deepest questions about existence. Are we alone in the grand scheme of things, or is every possible version of reality out there, whispering to us through the cracks in the math? Perpetual motion machines are supposed to be impossible, a fantasy dismissed by physicists for centuries. The laws of thermodynamics are clear. Energy can't be created from nothing, and every system eventually winds down. Yet in 2012, Nobel laureate Frank Wilczek proposed something that seemed to break these rules: time crystals, bizarre quantum structures that pulse rhythmically like cosmic metronomes forever without any energy input. Not only did they sound like science fiction, but by 2017, labs had actually built them. So how do these enigmatic crystals dance around thermodynamics, and what do they whisper about time's deepest secrets? Time crystals don't defy energy conservation, they cheat it. Unlike a hypothetical perpetual motion machine, which claims to generate energy endlessly, time crystals don't produce usable work. Instead, they exploit quantum loopholes to enter a state of non-equilibrium, where their atoms oscillate between configurations in a fixed, unending cycle. Picture a clock that ticks without springs or batteries, its hands moving solely because the universe's quantum rules allow it. This rhythmic behavior emerges from a phenomenon called breaking time translation symmetry. Normally, the laws of physics don't care when you perform an experiment today or tomorrow. Outcomes should be identical. But time crystals do care, locking into patterns that repeat at intervals unrelated to external forces, like a drumbeat only they can hear. Creating these crystals isn't about forging some exotic material, it's about choreographing quantum chaos. In groundbreaking experiments, researchers used chains of ytterbium ions or diamond defects, chilling them near absolute zero and nudging them with precisely timed laser pulses. The result, a system that, instead of settling into stillness like ordinary matter, flips between states indefinitely. It spins, synchronizing into a rhythm that persists even after the laser's off. It's as if you pushed a playground swing once and watched it keep swinging, not just for hours but for eternity. The implications ripple far beyond curiosity. Time crystals might revolutionize quantum computing by stabilizing qubits against decoherence, the noise that scrambles calculations. Their resilience against disturbances hints at new phases of matter, akin to how superconductors defy classical electrical resistance. But the real magic lies in what they suggest about time itself. Einstein showed time is relative, but time crystals imply it might also be emergent, a side effect of quantum systems interacting in ways we're only beginning to grasp. Could the arrow of time, the relentless march from past to future, be woven from countless microscopic ticks of these crystals, yet mysteries linger? Do time crystals truly last forever, or will quantum fluctuations eventually disrupt their beats? Can they exist at room temperature, or are they forever shackled to frigid labs? And most tantalizingly, if time is just another quantum variable, what other impossible-seeming states of matter might be hiding in the math, waiting to be uncovered? For now, time crystals stand as both a triumph and a riddle, proving that even in a universe bound by entropy, there are still ways to dance forever. Neutrinos are the universe's ultimate ghost particles, so elusive they can pass through a light year of lead without a trace. For decades, physicists assumed they were massless, zipping through space at the speed of light like tiny, chargeless photons. But then came the bombshell: neutrinos change identities mid-flight. A neutrino born in the heart of the Sun might start its journey as an electron neutrino, only to morph into a muon or tau neutrino by the time it reaches Earth. This bizarre phenomenon, called neutrino oscillation, proved these phantoms must have mass, a revelation so shocking it earned the 2015 Nobel Prize and ripped a hole in the standard model of particle physics. The question isn't just how much they weigh, it's why they weigh anything at all. The Standard Model, our most precise blueprint of the subatomic world, initially had no room for massive neutrinos. Its equations treated them as weightless, a tidy assumption that kept the math elegant. But nature doesn't care for elegance. Experiments like Super Kamiok and the Sudbury Neutrino Observatory caught neutrinos red-handed in the act of oscillation, a trick only possible if their masses differ slightly. Think of it like a cosmic sleight of hand. As neutrinos travel, their quantum states evolve, and the probability of detecting a particular flavor wobbles like a spinning coin. The catch: this wobble requires mass specifically, that at least 2 neutrino types have non-zero masses. The numbers are almost laughably small. The heaviest neutrino is at least 10 million times lighter than an electron. But even this whisper of mass is enough to upend physics. Where does this mass come from? The leading suspect is the seesaw mechanism, a theory where neutrinos' featherlight weights balance out hypothetical super-heavy particles we've yet to detect. Picture a playground seesaw with a sumo wrestler on one end and a toddler on the other, the heavier one side, the lighter the other. If sterile neutrinos, their elusive cousins, exist at unfathomably high energies, ordinary neutrinos could inherit their tiny masses through this cosmic balancing act. Another possibility is that neutrinos are their own antiparticles, a property that would force their masses to emerge from entirely different physics than other particles. The implications ripple far beyond particle physics. Neutrinos are relics from the Big Bang, and their mass shapes how galaxies cluster. Even their minuscule gravity subtly sculpts the cosmos, influencing the universe's fate. Experiments like Katrin are hunting for absolute neutrino masses by studying tritium decay, while detectors buried in Antarctic ice and abandoned mines wait for rare collisions that might reveal sterile neutrinos or other exotic twists. But here's the real kicker. Neutrinos could be the key to the universe's matter-antimatter imbalance. Their slight mass might have tipped the scales in the early cosmos, favoring matter over antimatter just enough to leave us with a universe full of stars, planets, and life. Solve the neutrino mass mystery, and we might finally understand why anything exists at all, not just as a fleeting quantum fluctuation, but as a lasting echo of the cosmos' deepest secrets. At the moment of the Big Bang, the universe was compressed into an infinitely dense, infinitely hot singularity, a point where all known laws of physics shatter. General relativity, our most robust theory of gravity, describes spacetime as a smooth fabric bending under mass and energy. But at t equals 0, those equations spit out nonsense: infinite curvature, infinite density, infinite everything. It's as if the universe handed us a birth certificate with the most critical line blacked out. This isn't just a gap in our knowledge, it's a fundamental rupture in reality's blueprint. So how do we peer past the veil of time's beginning? The answer might lie in rewriting physics itself. Enter loop quantum gravity, a daring framework that reimagines spacetime not as continuous, but as woven from tiny, indivisible loops. Think of it as the universe's pixelated underpainting. In this view, the Big Bang wasn't a true singularity but a big bounce, where a previous collapsing universe rebounded into ours. Picture spacetime as a sponge. Squeeze it too hard, and quantum pressure kicks in, preventing total collapse. The equations suggest a minimum volume below which space cannot shrink, sidestepping infinity entirely. If correct, our universe might be just the latest chapter in an endless cycle of expansion and contraction, with no true beginning or end. String theory offers another escape hatch. By proposing that particles are vibrating strings in 10 or 11 dimensions, it smooths out the mathematical jaggedness of singularities. In some string cosmologies, our Big Bang could have been a collision between higher dimensional brains like sheets of reality slapping together in a cosmic high five. The energy of that impact might have ignited our universe with no singularity required. Others speculate that time itself emerges from these strings interactions, meaning, before the Big Bang, could be as meaningless as asking what's north of the North Pole. Yet the most radical ideas come from quantum cosmology. The no-boundary proposal by Hawking and Hartle treats the universe's origin like the Earth's South Pole. There's no edge, just a smooth rounding off where time transitions into space. Imagine a globe where the Big Bang sits at the pole every before direction points toward it, but there's no actual point of creation, just a geometric necessity. Meanwhile, causal set theory suggests space-time is built from discrete atoms of causality, where time emerges from the sequence of events like frames in a movie reel. In this view, the question, what happened before, might be like asking what's outside a video game's code. The framework itself defines the rules of existence. The stakes couldn't be higher. If we crack the singularity, we might learn whether our universe is one of many in a vast multiverse, or if time itself is an illusion woven from deeper quantum threads. Current experiments like hunting for primordial gravitational waves or anomalies in the cosmic microwave background could carry faint echoes of that first moment. Until then, the singularity remains the ultimate cosmic cliffhanger, a reminder that even the universe has secrets it isn't ready to share. From the speed of light bending around black holes to the ghostly whispers of dark matter shaping galaxies, these 30 riddles aren't just gaps in our knowledge, they're invitations. Each one is a doorway to a deeper understanding, a reminder that the universe thrives on mystery. Think about it, every time we've unraveled one cosmic secret, like the true nature of stars or the fabric of space-time, we've stumbled upon 10 new questions even more baffling than the last. That's not a failure of science, it's the heartbeat of discovery. What makes these puzzles so exhilarating isn't just their complexity, but the way they connect. The same quantum weirdness that leaves particles entangled across light years might hold clues to black holes' information paradox. The vacuum's hidden energy could be tangled up with why the universe is expanding faster than we predicted. It's as if the cosmos is a grand puzzle box where solving one piece twists another into place, revealing patterns we never expected. And the most thrilling part, some of these answers might be within our grasp in your lifetime. The next groundbreaking paper, the next revolutionary telescope, the next eureka moment in a lab somewhere, it could all come from someone watching this right now, armed with nothing but curiosity and the courage to question. So here's your challenge. Don't just marvel at these mysteries, own them. Talk about them, debate them, let them keep you up at night. Share your wildest theories in the comments. We've all wondered if dark energy is an alien experiment or if wormholes are hiding in plain sight. And if you're craving more deep dives into the cosmos' greatest enigmas, hit like, subscribe, and join us as we keep chasing the next revelation. Because the universe isn't just a story, it's a conversation, and your voice belongs in it. After all, the greatest discoveries start with someone looking up at the stars and asking, what if? Until next time, keep wondering. The cosmos has plenty more secrets